Have you ever stopped to consider how crucial understanding heat transfer is to our everyday lives? From the operation of our vehicles to the heating of our homes, the principles of heat transfer are at work. Today we delve into the fascinating world of heat, exploring the results of several pivotal experiments. Our journey begins with the study of heat transfer through a composite wall. The objective here was to comprehend how heat travels through different materials layered together. The findings were enlightening, revealing that heat transfer rates differ depending on the material properties, thickness, and arrangement. This knowledge is fundamental in the manufacturing of insulated products, where controlling heat flow is paramount. Next, we ventured into the study of heat transfer through a lagged pipe. This experiment sought to understand how insulation affects the rate of heat transfer. It was discovered that insulation significantly reduces heat loss, a principle used widely in the maintenance of temperature in piping systems across various industries. Moving on, we investigated heat transfer through a fin. Here, the goal was to ascertain how fins enhance heat dissipation. The experiment confirmed that fins, due to their increased surface area, drastically improve heat dissipation, a principle leveraged in countless cooling systems, from computer processors to car radiators. The study of the unsteady state of heat transfer was next. This experiment aimed to understand how heat transfer occurs when the temperature is not constant. The findings showed that heat transfer is dynamic and changes over time, a critical insight for the design of systems that experience fluctuating temperatures, like heating and cooling systems in buildings. Then, we explored heat transfer in forced convection. The objective was to understand how forced movement of fluid influences heat transfer. The results indicated that forced convection significantly enhances heat transfer, a principle that finds application in various cooling and heating systems, such as air conditioning units and boilers. Following this, we examined heat transfer in natural convection. This experiment aimed to investigate how heat transfer occurs when fluid motion is caused by temperature differences. The findings revealed that heat transfer is slower in natural convection compared to forced convection. This understanding is essential in the design of systems where natural convection is the primary mode of heat transfer, such as solar water heaters. Next was the heat transfer study in parallel flow, counterflow heat exchanger walls. This experiment aimed to compare the efficiency of the two types of flow. It was found that counterflow is more efficient than parallel flow, a principle that informs the design of heat exchangers in various industries. Subsequently, we studied heat transfer through a fin tube heat exchanger. The objective here was to understand how fins enhance heat transfer in a tube exchanger. The results confirmed that fins significantly improve heat exchange, a principle applied in many heat exchanger designs. Next, we ventured into the heat transfer study in a shell and tube heat exchanger. The goal here was to understand how heat transfer occurs in this type of exchanger. The findings showed that the shell and tube design is highly efficient for heat exchange, a principle used in a wide range of applications, from power plants to refrigeration systems. The study of critical heat flux in boiling followed. This experiment aimed to identify the point at which a surface gets so hot that a vapor layer forms, reducing heat transfer. The results pinpointed the critical heat flux point, which is vital in the design of systems that involve boiling, such as power plant boilers. Finally, we embarked on the determination of the Stefan Boltzmann constant experimentally. This experiment aimed to calculate the constant that relates a body's temperature to its thermal radiation. The results provided an experimental value for this constant, a key parameter in the field of radiative heat transfer. In summary, these experiments shed light on the complex and fascinating phenomena of heat transfer. They highlight the importance of understanding these principles, as they are integral in the design of countless systems that we rely on daily. From the insulation in your home to the cooling system in your computer, heat transfer plays a pivotal role. So, the next time you feel the warmth of a heater or the cool breeze of an air conditioner, remember the science behind it. It's all about heat transfer.